Bismillahirrahmanirrahim. Assalamu alaikum. Lecture number 10, unit number 2. The title of unit number 2 is Matrices and Determinant. The topic of this video lecture is row and column operations on matrices, echelon and reduced echelon form of a matrix. First of all, we will discuss the row operations on matrices. Row operations on matrices. First of all, we will discuss this. There are 6 operations, or you can say 6 transformations on matrices, 3 of which are due to rows and 3 due to columns, which are known as elementary operations or transformations. So there are 3 elementary row operations and there are 3 elementary column operations on matrices. These operations are also called transformations. So first of all, we will discuss the row operations on a matrix. You can interchange any 2 rows. You can interchange any 2 rows. Okay, now you see that the first elementary row operations on matrices is interchange of any 2 rows. And note, if you are interchanging Ri row and Rj row, so this is the symbolic representation of the interchanging of Ri and Rj row. So let's say, for example, if we consider an example, this is an example. I am considering this example, and first I am converting R1 and R2. So this is the symbolic representation. That this symbolic representation means that you are required to interchange row 1 and row 2 of the given matrix. So let's say you see that this is the given matrix and I am interchanging R1 and R2. So R2 will be written in place of R1 and R1 will be written in place of R2. So let's say this is a matrix B. So this matrix B is obtained by performing this row operations. R1 interchanged into R2. These are the row operations are done in this matrix to get this matrix. When you perform a finite number of row operations and get another matrix, that matrix is said to be row equivalent to this matrix. So this matrix B is row equivalent to matrix A. Now these are the row equivalent matrices. Now the notations, the writing for row equivalent matrix is B is row equivalent to A, and this equivalent matrix is obtained by performing row operations. So that's why I write R here. This is the symbolic representation. Okay, the next row operation is multiplication of a row by any non-zero scalar. Any row can be multiplied with any non-zero scalar. For example, Ri is the row and you are multiplying that row with a non-zero. Remember that scalar must be non-zero. So the value of k must be non-zero real number. You can multiply with any row. So this is the symbolic representation of this. For example, now in this matrix, let's say I multiplying row 3 by 4. So that matrix will become row 1 will be written as it is, row 2 will be written as it is, and row 3 will be multiplied with 4. So that 4 will be multiplied with every element of that row. So minus 4, minus 16. So this matrix, this is row equivalent to this matrix, and this matrix is obtained by row operation, which is we multiply 4 with the third row. So this is the second row operations. You can multiply any row by any non-zero scalar, and this is the symbolic representation of that. Okay, the third one, addition of any multiple of one row. Any multiple of one row mean scalar multiplication of a row by non-zero scalar make the row multiple of the original row. You see that this third row in this equivalent matrix of this is actually the multiple of this row, because this minus 4 can be written as the product of 4 and minus 1. This minus 16 can be written as a product of minus 4 and 4. So actually this row, which is obtained by row operation, that is multiply a row by non-zero scalar, is actually you obtain a row multiple of this. So you can add a row multiple of one row to any other row. Addition of any multiple of one row to another row. So you see that this is a row multiple of this. Now you can add this to any one of the matrix. So this row equivalent, now I am adding R1 plus 4R3. So you see that this 4R3 is actually the multiple of the row number 3. So the third row operation is addition of any multiple of one row to another row. So you are adding, so you see that this will be written in in its own place, the second will be on, and I am adding this with the R1. So R1 will become minus 3 and that will become minus 14, because 1 plus minus 4 mean 1 minus 4 minus 3, 2 plus minus 16 equal to minus 14. So this is the third row operations. If you multiply 1 to some row, so that is also called multiple of one row. So if the scalar multiplication where k is equal to 1, so in that case that will be the addition of two rows in that matrix. So the addition of two rows in a matrix is also possible. So these are the three row operations. Okay, now for the column operations, you just need to replace this row by column. Now I am discussing the column operations. So columns, you can interchange any two columns, and the symbolic representation for that will be this. You can interchange any two columns. Now the second, for example, this is a matrix, this is a matrix, so you can interchange any two rows, so any two columns. So there are two columns, so this is column number 1, this is column number 2, so you can interchange column 1 and column 2, and the representation for this will be Ci double-headed arrow C1 C2. So this means that you are interchanging C1 and C2. So in elementary column operations, you can interchange any two columns. You can also multiply a column by any non-zero scalar, and the representation for that will be K Ci. C is for the column. And you can also add any multiple of one column to another column, and the notation, the symbolic representation for that will be R Cj plus KCi. You see that this KCi is actually the scalar multiple of the row of the column Ci. So any multiple of one column can be added to another column. So these are the three column operations. These are the three rows operation, and these are the three column operations. Now when a matrix is obtained by finite numbers of row operations or by doing finite numbers of column operations, so the matrix which you obtained is said to be row equivalent to the original matrix. Row equivalent if you do the elementary row operations, and if you do the elementary column operations, so then that matrix is said to be column equivalent matrix to the original matrix. So this is an example in which you see that we need to perform the row operation R2 plus 2 R1. So this is the original matrix, 1 2 3 5 minus 1 minus 4. Now the first row operation is you need to multiply R2 by 1, R1 by 2. You see that 2 multiplied by R1, so 2 multiplied by R1, so this will become 2 4 3 5 minus 1 minus 4. Then the next row operation will be, okay, now you get this. You need to write this in the on the side, in the rough. Actually we are doing this row operation, so R2 plus 2 R1. So now this must be written in its own place. Now if you are converting this, so that will be written 1 2, this is minus 1 5, and 2 R1 is added to R2, so this is 3, this is 2 R1 is actually 2, and 5 2 R1 here is 2. So that matrix which you obtain, this is 1 2 5 7 minus 1 5, is row equivalent to the original matrix. Let's say this matrix is named by B, so this matrix B is row equivalent to matrix A, because this matrix B is obtained by performing finite numbers of row operations. So that's why this must be a row equivalent. Similarly, you can do the remaining. C2 minus C1 means actually C2 plus minus 1 times C1. So you see that this is the addition of a multiple of C1 to C2. So you are adding two columns in which one column is actually a multiple of some other column. So first of all you need to multiply the C1 with minus 1 and then add C2 with minus C1. Or you can also do these operations at a single step. Here you will write C equivalent C. Now you see that this C1 will be written in its own place. C2 you are adding minus times C1 with C2, so this is actually C2, and you are adding minus times C1, minus times C1. So this is the C2 plus minus times C1, or you can write it C2 minus C1. So this column equivalent matrix will be equal to 2 minus 1, this is 1, 5 minus 3 2, minus 4 plus 1, so minus 3. So this is a matrix which you obtain by performing this column operation. So this matrix is said to be column equivalent to the original matrix, because this is obtained by doing finite numbers of column operations. So these are row operations and column operations. Now after row operations and column operations, the next topic is echelon and reduced echelon form of a matrix. But before to discuss that, you see this note: a matrix A is an m by n matrix. Let's say the order of the A is m by n, then an m by n matrix, this is another matrix having the same order, is obtained from the original matrix by performing finite numbers of elementary row operations or column operations. on A is called row equivalent to A, and if you perform the elementary column operation, so that will be called column equivalent to matrix A. And symbolically, for row equivalent matrix, B will be row equivalent to matrix A, and if you perform the column operations, so that matrix B will be column equivalent to matrix A. But remember, these 6 are the elementary row operations on columns, row operations on and column operations on matrices. These elementary row operations are used to find out the echelon and reduce echelon form of a matrix. So these are important row and column operations. You cannot do any other operation instead of these in a matrix with a row or with a column. So these row operations and column operations are used to find out the echelon and reduce echelon form of a matrix. So what is echelon and what is reduce echelon form of a matrix? Echelon form of a matrix. In each successive non-zero row, the number of zeros before the first non-zero entry of a row increases row by row. So what does it mean? Every non-zero row in A precedes every zero row. So what does it mean? These, if a matrix satisfies a matrix, let's say we have a matrix of order m by n, and that matrix satisfies these two conditions, then that matrix is said to be in row echelon form if these two properties are satisfied. Okay, I am considering an example to explain these 2 points. The example number 1 is, this is 2 3 minus 4 1 0 1 5 3 0 0 0 6. If someone asks from you that is this matrix in the echelon form or is not in the echelon form, so how you can check the matrix is in echelon form or the matrix is not in the echelon form? The first step is you need to search for the first non-zero row. So the first step will be you will search in the given matrix that row number 1 is the non-zero row, first non-zero row, or row number 2 is the first non-zero row, or row number 3 is the first non-zero row, and so on. The non-zero row means at least one of the entry in that row is non-zero. So first of all, you will search for first non-zero row. In this case, R1 is the first non-zero row. You see that this R1 contain more than one non-zero entry. So this is the first non-zero row. Now in first non-zero row, you will search the first non-zero entry. So this is your first non-zero entry. This is your first non-zero entry. And now you will count the number of zeros before the first non-zero entry. So this is the first non-zero entry, and before the first non-zero entry in the first non-zero row, the number of zeros are 0. Mean there is no 0 to the left of the first non-zero row in the first to the first non-zero entry of the first non-zero row. Okay, so in first non-zero row, the number of zeros to the left of first non-zero entry is 0. So this number must be increased row by row, that in second row, this is your first, this is second non-zero row, this is second non-zero row. In second non-zero row, this is your first non-zero entry. So here before the first non-zero entry there is no zero. So here before the first non-zero entry there are 1 0, and here this is also the third non-zero row, and here also you see that before the non-zero entry the number of zeros are more than the previous row. So this means that in each successive non-zero row, so you see that after one R1 there is R2, there is R3. So these are the successive rows. In these successive rows, the number of zeros before the first non-zero entry of a row increases row by row. So here before the first non-zero entry the number of zeros are 0, and after that in the second non-zero row the number of the zeros before the first non-zero entry are more than the first row. And similarly you see that in the third non-zero row the number of the zeros are increased before the first non-zero entry is of R2. So this is the meaning of this. You see that in each successive row the number of the zeros are increases row by row. You see that here is before the first non-zero entry there is no 0. In the second before the first non-zero entry there is 1 0. In third in the first before the first non-zero entry there are 3 rows. So you see that the number of the zeros before the first non-zero entry in a non-zero row is increasing row by row. There is no 0, there is 1 0, there is 3 zeros. So this is condition number 1. This condition number 1 is true in matrix A. The second condition is every non-zero row in a matrix A precede every zero row. It means that if there is a zero row in which all the entries are 0, so that zero row must be written at the last, mean that zero row must be the last row. But there is no zero row, so for such type of matrices you will just check this point number 1, and this point number 1 is true for matrix A, and the point number 2 there is no zero row, so we didn't need to check the point number 2. So this implies that the matrix A is in the echelon form. Now if I consider a second example, let's say this is a matrix B and this is 0 2 3 0 0 minus 5 0 0 0. So now this is your first non-zero row. You will first see to the first non-zero row. This is the first non-zero row, and this is your first non-zero entry. So before the first non-zero entry there is only 1 0. Now in the second non-zero row before the first non-zero entries the number of the zeros are increased. So point number 1 is satisfied, and you see to the third row this is a 0 row, and that 0 row is written at the end of the rows, mean this is the last row of this matrix. So point number 2 is also satisfied. So this matrix B is in row echelon form. Row echelon form. This is the way to check a matrix is in the row echelon form or not in a row echelon form. Now I am considering another example to verify, to explain the points a little more. 0 0 1 2 0 1 2 3 0 0 0 1. Let's say this is a matrix C. So this is your first non-zero row. In first non-zero row this is your first non-zero entry. Before the first non-zero entry there are 2 zeros. Now this is your second non-zero row. In second non-zero row the first non-zero entry is 1. This is, and before that non-zero entry there are 1 0. So it means that in the coming non-zero row the number of the zeros that is present before the first non-zero entry in the first non-zero row are not increased. So condition number 1 is not satisfied. So that's why this matrix is not in the reduced echelon form. C is not in C is not in row echelon form. So how you can convert that matrix into row echelon form? We will perform the elementary row operations and elementary column operations. So if I interchange the first row and second row in this matrix, you see that this is not in the row echelon form, but we study row operations and column operations. In row operations, we know that you can interchange any two rows, you can multiply a non-zero row, you can multiply a non-zero row by a non-zero scalar, and you can also add one row to another row, but that row must be some multiple of a row, mean adding a multiple of one row to another row. So these row operations are possible as well as column operations. So if I interchange, let's say I am finding the row equivalent matrix of this, and I am interchanging R1 and R2. So you see that the R2 will be written in place of R1 and R1 be written in place of R2. So now you see that this matrix is in the echelon form because this is the first non-zero row. In first non-zero row, the first non-zero entry is this. Before the first non-zero entry, there is 1 0. This is the second non-zero row. Before the first non-zero entry, there are 2 rows, so the number of the zeros are increased. There is the third non-zero row. This is the first non-zero entry of the third non-zero row. Before that, there are 3 zeros, so it means that the number of zeros from the previous row increases. So you see that this matrix satisfies the condition number 1 for echelon form of a matrix or row echelon form of matrix, and there is no zero row, so you didn't need to check the condition number 2. So this matrix is now in echelon form. This is in row echelon form. So row operations and column operations are used to convert a matrix into row echelon form. So you see that by row operations we convert a non-row echelon form matrix to a row echelon form matrix. Now the next is reduced echelon form of a matrix. A matrix is said to be in reduced echelon form if it is in the echelon form, and the second condition that the first non-zero entry of the first non-zero row, let's say Ri is the first non-zero row, and that first non-zero entry must be lying in some column. You see that I am taking an example and explaining this. 0 1 0 2 0 0 1 3 0 0 0 0. So you see that first of all you need to check that the given matrix in the echelon form. If you are checking that the given matrix in the reduced row echelon form, so first of all you need to check that the given matrix in the echelon form. So for the echelon form, you will search for the first non-zero row. So this is your first non-zero row. In this first non-zero row, this is your first non-zero entry. Before the first non-zero entry, the number of zeros are 1, and that number of zeros, the number of the zeros must be increased in the preceding rows. So you see that this is the second non-zero row, this is the first non-zero entry of the second non-zero row. The number of the zeros are increased. You see there are 2 zeros, and there is no other non-zero row, and you see that this is the 0 row which is written at the end of the rows. So this matrix A satisfies the 2 condition of the echelon form of a matrix. So this matrix A is in the echelon form. So this is the point number 1 for the reduced echelon form of a matrix. This is true. Now the second point. The second point says that in the first non-zero row, the first non-zero entry, which is this one, this is your first non-zero row, and this is your first non-zero entry. This is your first non-zero entry, which lies in C2. You see that this Ri, in which the first non-zero entry is 1 is lies in some column. So you see that this is the column in which the first non-zero entry of the first non-zero row lies. So this first non-zero entry must be 1, and in the column the rest of the elements must be 0. This one is called pivot element, and the column in which the pivot element lies is said to be pivot column. Now this must be true for every non-zero entry. It means that if a matrix is in echelon form, so the second condition says for the reduced echelon form that the first non-zero entry of every non-zero row must be 1. So you see that this is 1, and the column in which that 1 lies, the rest of the elements must be 0. So here are 0. Now moving towards the second non-zero row. In second non-zero row, the first non-zero entry will also be 1. So this is 1, and the rest of the elements in that column must also be 0. So this is also true in there, and there is no other non-zero row. So the condition 2 is also satisfied in this matrix. So this matrix is said to be in reduced echelon form, or you can say reduced row echelon form. I am taking another example to explain the reduced echelon form of a matrix. You see, this is another example. First of all, I need to check that the given matrix is in echelon form or not. This is the first condition for the reduced row echelon form. So echelon form, row echelon form. So first of all, I row echelon form, or you just need to write echelon form. So this matrix A is in the echelon form. Why? You need to check the 2 points of the echelon form. This is your first non-zero row. The first non-zero entry is 1. Before the first non-zero entry there is no 0. Now this is the second non-zero row. This is the first non-zero entry of the second non-zero row. Before that there is 1 0. So the number of the zeros are increased. This is the third non-zero row, and this is the first non-zero entry, and before the first non-zero entry there are 3 zeros. So you see that the number of the zeros before the first non-zero entry in the non-zero row are increasing row by row. So the condition 1 is satisfied, and the fourth row is a 0 row, and the 0 row is written in the at the end. So this is in the echelon form. This is condition number 1 for the reduced echelon form. I am checking that the matrix is in the reduced echelon form or not. Reduced echelon form. Okay, reduced echelon form. Now step number 2. Step 2 says that if in a first non-zero entry, in a first non-zero row, the first non-zero entry must be 1. So you see that here the first non-zero entry is 1. This is the first non-zero row. The first non-zero entry is 1, and that entry lies in C1, and the rest of the elements of that C1 is 0. So you see that they are 0. Satisfied. Move to second non-zero row. In second non-zero row, the first non-zero entry is 1, and the rest of the elements in that column is 0. Now move to the third non-zero row. The first non-zero entry is 1, and the rest of the elements in that column are 0. So this matrix also satisfies the condition 2 for the reduced echelon form, and this matrix is in the reduced echelon form. Now if I consider another matrix 0 1 0 3 0 0 1 2 0 0 0 4. First of all, I will check that this is in the echelon form or not. So this is the first non-zero row. In first non-zero row, this is the first non-zero entry. This first non-zero entry in the echelon form may be any number, but in the reduced echelon form that must be 1. But in the echelon form that may be any number. So this is your first non-zero entry. Before the first non-zero entry, the number of zeros are 1. The second non-zero the first non-zero entry of the second non-zero, the number of the zeros are 2, mean increased, and this is the third non-zero row in which this is the first non-zero entry and the number of zeros are 3. So it means that row by row the number of the zeros before the non-zero row, the non-zero entry are increased. So this is in the echelon form. Now moving for the reduced echelon form, there is no zero row, so you didn't need to check the condition 2 for the echelon form. Now this is in the echelon form. This is in the echelon form. Now checking the second condition. In second condition says that the first non-zero entry of the first non-zero row must be 1. So this is 1 and the rest of the elements of that column must be 0. So this is 0. This is true. For the second non-zero row, the first non-zero entry must be 1 and the rest of the elements in that column must be 0. That is true. Now this is the third non-zero row. You will check that condition for every non-zero row. So in third non-zero row, the first non-zero entry is not 1 and the rest of the elements are also non-zero. So that's why this is not in the reduced echelon form. This is in the echelon form but not in the reduced echelon form. A is in the echelon form but not in the reduced echelon form. Okay, so we can do a row operations or a column operations to convert the matrix into reduced echelon form, and those 6 row and column operations will be used to convert a matrix into reduced and row echelon form. Okay, what is the rank of a matrix? This is the last topic of this video lecture. Rank of a matrix, the number of the zeros in the echelon form of a matrix. For example, if I consider a matrix in the echelon form, you see that this matrix is in the echelon form, you see it here. So the number of the non-zero rows of a matrix in the echelon form, the definition of the rank is rank of a matrix. So rank of the matrix is number of the non-zero rows, number of the non-zero row mean at least one of the element is non-zero. So number of the non-zero rows, number of the non-zero rows in the echelon form, in the, or you can say row echelon form of a matrix. So this matrix is in the echelon form. First of all, you need to convert the matrix in the echelon form when you are finding out the rank. So this matrix is in the echelon form and the number of the non-zero rows are 3. So the rank of this matrix is equal to 3. Okay, the echelon form and reduced echelon form are used to find out the or you can say that the elementary row operations and column operations are used to find out the inverse of a matrix. But if you see to the exercise 2.3, in this question you need to convert this into the echelon form. So what you can do, you need to you need to perform row operations and column operations. So this is already you need to make the first non-zero entry 1. So this is also this is already 1. So you need to and before the first non-zero entry the number of zeros are 0. So you need to make 1 0 in this row. So if I multiply R1 by 2 and then subtract R2 from R1, so this will become 0. So this second row will contain 1 0 before the first non-zero entry, and in the third row we need 2 non-zero rows before the first non-zero entry. So you can do the row operations to convert the matrix in the echelon form. In the reduced echelon form, you need to convert the given matrix into the echelon form, and then the first non-zero entry in the first non-zero row must be 1 and the rest of the elements of that column are zeros, and that will be true for all the non-zero rows. So you can convert this matrix into echelon form. This is into row echelon, reduced echelon form. This is into reduced echelon form, and this is into echelon form. Now question number 3 says that find out the rank of the following matrices. So rank of the following matrices, you need to convert the given matrices into echelon form and then count the non-zero rows. And so you need to do all these questions. This is assignment number 4. This is assignment number 4, and assignment the question 2 is left. You didn't need to find out the inverse. This can be discussed in next video lecture. So this is assignment number 4. The date for the submission is 1st August 2020. This is assignment number 4. You can watch the video again and again to learn the row and column operations and the echelon and reduced echelon form of a matrix, and then you need to perform the row and column operations to convert the this matrix into echelon form. This is into reduced echelon form, and so on. And if you are finding the rank of a matrix, so rank of a matrix is equal to the non-zero rows in the row echelon form. So this is exercise 2.3. okay. Exercise 2.4, we will discuss theoretical work in coming video lecture. Thank you.